Hi everyone, I'm Min. This presentation is a summary of my report on data center networking. So for the full information, please read the report. Some background information before I proceed further. In the past, our applications only used to run on one server. However, with multi-tiered applications, microservices, and cloud computing, there are more requirements for modern DC. Due to quality of service, increasing demands, and distributed data centers, reliability, low latency, scalability, and central management has become important for modern DCs. Amazon, Microsoft, and Google have their ways to address these. They are using clause topology for their network and software-defined networking for network management. These will be the main focuses for today. Firstly, clause topology. Instead of the typical core aggregate edge architecture, clause uses the leaf-spine architecture. The figure on the left shows a 3-stage clause network, which can be converted into a 5-stage clause network on the right. If we fold this network, we will get a clause network like this. Comparing the clause network to a tree-based network, we notice that the clause network has more switches and connections than a tree-based with redundancy. So why clause for modern DCs? Firstly, clause provides more reliability through path diversity. If one spine switch is down, the degradation is 0.25, as the remaining 3 spine switches will share the load. However, for a tree-based topology, if a core switch is down, the degradation will be 0.5, with the remaining core switch handling all the traffic. Clause is also optimized for east-west traffic. East-west traffic refers to intra-DC traffic. In modern data centers, for example, different microservices may reside within the same DC, but in different segments, and the communication between these microservices will be east-west traffic. In a tree-based topology, we can tell that the number of hops differ depending on the edge switches, and this causes latency differences. However, in clause, the number of hops is the same regardless of the leaf switch, unless leaf switches are connected to the same tier 2 spine. Hence, it is more optimized for east-west traffic. Lastly, scalability. In clause, it is easy to scale horizontally. One can just add more leaf switches until the ports on the spine switches are all used, or add more spine switches. In a tree base, it is not as easy to scale horizontally because adding a device will affect the structure of the other devices in the network due to the strict hierarchy. Next, software-defined networking. In network devices, the control plane and the data plane are often tightly coupled together. When we provide a layer of abstraction over these network devices, we can decouple the data and control planes. In SDN, the data plane contains the forwarding devices, which are the switches. These forwarding devices are controlled by software controllers in the control plane through APIs and the southbound interface. OpenFlow is widely regarded as a standard for SDN, as it dictates the protocol to be used between the control and the data plane. Flow rules that decide how network packets will be processed are stored on the forwarding devices, and the controller manipulates the flow rules stored inside these forwarding devices. There is also a management plane where the network management applications reside. These applications are often self-developed and they can interact with the controllers through the APIs and the northbound interface. SDN provides global control as a network administrator would be able to centrally configure network devices using the network management application that interacts with the SDN controllers. SDN also provides flexible routing. For customers who paid more for higher QoS, special routes might need to be configured to ensure that QoS requirements are met. And with SDN, routes can be easily configured without interacting with the network devices directly. SDN also has its drawbacks. The first is control traffic overhead. If flow rules change very frequently, the control traffic overhead will be high and may affect the throughput of the user traffic. The next is the cost. SDN-enabled switches are more expensive. To replace all traditional switches with SDN-enabled ones will cost a lot of money. What if we implement hybrid SDN, where SDN is only applied to a part of the network? While this might seem to lower the impact of the drawbacks, it brings new issues, such as how to determine the areas to have SDN applied and getting SDN controllers to work with non-SDN enabled devices. There are still areas for research for data center networking. The first is how a DC can better support the increasing demands for AI/ML computing. These often require a lot of GPUs and are not found in large quantities on servers in DCs as they are used for general processing. Another area for research will be on the sustainability of data centers. Data centers are expected to use more and more electricity, with environmental issues such as depleting fossil fuels, we will need to find new ways to make DCs more power efficient. In conclusion, clause-based networks and SDN supports the current needs of the data centers, but more research needs to be done to meet the demands of AI/ML computing and other developments. Thank you.